Welcome to C++ Forever, Interactive Applications in the Age of Manycore. My name is Rick Malloy. I'm a program manager on Microsoft's parallel computing platform. Specifically, I spend almost every minute of every day at work thinking about the concurrency runtime and our parallel programming models. What I want to do today is start off with a demo. After the demo, we're going to go through and I'll tell you sort of the agenda, the takeaways, that sort of thing. But first, I want to show you this little app that someone in our audience built. His name is Kenneth Bedstead, and this is a demo called the Flat 6 demo. So what we're seeing here, this is my little quad-core laptop, is we're seeing a 60 megapixel image being processed in basically real time. It's getting about 10 megapixels a second, so the frames are turning a little bit slowly on this four-way. But remember, this image is massive. It's a RAW format, so it's doing all the transcoding. It's doing very high-quality SSC-optimized filters on it. We had some connectivity issues. I was going to show this live on a high core count box. If you go down to AMD's booth, you can actually see it there in the pavilion. But I'll show you a screenshot of it running after I close it that I took over the weekend on a different box. And so this is the same application, the same binary running on a 64 processor computer. This application basically scales linearly. If you get a 2x speed up on a two-way, a 4x speed up on a four-way, an 8x speed up on an 8-way, a 48x speed up on a 48-way, and a 64x speed up on a 48-way. This is the thing we want to try and unlock. This is that free lunch that went away that we want to re-enable. So that's what this talk is about. So specifically, what I want you guys to walk away from this is that expressing concurrency is easier in C++. We can talk about tasks, parallel loops, build concurrent pipelines so you can actually stream data through a pipeline, apply tasks to each stage of that pipeline and get speedups there. You can actually nest inside that stage of that parallel pipeline a parallel loop and not see penalties from oversubscription or from that sort of composability of concurrency. You can build your own parallel patterns, and I'll build a couple of very simple loops here, or one, and show you another one that I built literally in 5 minutes yesterday. I'll demonstrate the composable and scalable concurrency runtime. I'm not going to talk in depth about the runtime itself. I'll let Dana talk about that Thursday morning at 8:30 in a server track, but we will see it. Because what I want all of you to do is focus on correctness, not scalability. Focus on describing the concurrency in your application, worrying about those race conditions, those of you that were at that talk just before this, and not worrying as much about, gee, is this actually going to perform on the broad range of hardware we have in the market today? Just a quick question. How many people are using a single core box as their primary development box or their primary user box? None. One. Great. Dual core. Quad core. This is where I fall. Anybody have some of the 8-ways? So this is a broad mix, really. We're seeing everything from 2 cores to 8 cores to 16 cores to, in some cases, the 48 processor and the 64-way processor way boxes. And finally, 2 more things. I want to talk a little bit about managing shared state. So we'll talk about some of the locks and the concurrent containers in the programming model. And we'll also talk about how to avoid that shared state and do some different things via message passing in the agents library. And throughout this, as I'm doing demos, I'll be showing you the tooling enhancements we've made to Visual Studio 2010 so you can actually navigate your parallel program or your multi-threaded program, optimize it, profile it, and actually make a little bit more sense out of this thing that's going on. Great. And so just to sort of ground things out, this is what Visual Studio 2010 looks like as far as parallelism is concerned. We have a very rich managed library. We've got some incubation work with Axum, with Visual F#. We've got some managed libraries, Parallel Link, the task parallel library. There's a very rich set of managed data structures. This is all in .NET 4. And then on the native side, which is what this talk is focuses about, We have the parallel pattern library, the asynchronous agents library, and a set of concurrent data structures. We also have the concurrency runtime, which is actually a platform for concurrency, which, as I mentioned, Dana will be talking about Thursday. It has a rich task scheduler, and it has a rich resource manager, where the primary resource it manages is CPU resources. And finally, on top of the operating system, there's a new feature in Windows 7 called UMS Threads that's only available in 64-bit, which we take advantage of. We also take advantage of greater than 64 proc support in the concurrency runtime, so you don't have to worry about it. Right? You can see some of these parallel 4s just working on the 64-way box. When Kenneth's team was building that demo, they didn't worry about how many cores were on the machine. And the native talks that are relevant, Dana's talk is SVR10. We've got SVR18, I believe, right after this one, and SVR01, which might even be the same time as this one right now. Okay, so that's sort of it for the high-level overview. My hope is to spend the majority of the rest of the time actually in Visual Studio or talking about things in Visual Studio. So when we talk about the parallel pattern library, there's a few key concepts that are important. The most important concept is the concept of a task. This is some body of work that you can schedule asynchronously. You can say, here's some work, I want you to schedule it. I might actually have multiple tasks, and I'll collect them together into a task group. So now I have a set of tasks. This set of tasks can be scheduled together. You can wait for them together, or you can cancel them together. I know Boris said just a couple minutes ago that people were asking about how cancellation worked. I'll explain it in detail, but the high level is when we cancel a set of tasks in a task group, that will not run any tasks that aren't started yet, and that will set a flag that tasks that are running can check. So it's sort of a very much an opt-in cancellation, but it can be very performant, particularly when it's composed together, because the cancellation can actually nest. Right? So if you have a set of loops that are chained together, you can actually cancel the whole tree, which can be very wonderful. And finally, as I was talking about parallel loops, so this is a way to talk about a set of operations, a parallel for, a parallel for each. You'll see some things. We actually put out a sample pack which has parallel accumulate, parallel partial sum, parallel transform, a good amount of things. And we'll see parallel any of and parallel count if today as well. These are all STL style algorithms. It doesn't preclude you from writing other interfaces, but as far as the parallel pattern library goes, the look and feel of the programming model is matched as closely as we could to the STL. Okay, so some demos. We're going to see how to express tasks in Visual Studio. I'm going to show you the debugger windows, so the tasks window and the parallel stacks window. Okay, so let's head over to my laptop, which is still running this screen here. Great. So here's a short little program. All of the code in the PPL is in ppl.h. All of the code in agents is in agents.h. There's not very many header files. Most of our patterns and classes that you'll see today are in the concurrency namespace. Sometimes I'll use some things from the concurrency samples namespace, and these are things that are in our sample pack online. How familiar are folks with C++ OX? Hopefully pretty familiar. Yeah, it's OK. So this funny syntax here, this is called a lambda. If you're used to C#, it's like a delegate, but I can say, here's a class. Think of it as a wrapper around a functor object. Between the angle brackets, I can capture state. Between the parentheses, I can describe the parameters. And between the curly braces are the statements that I run. It's really just some loose syntax, some syntactic sugar, so to speak, for describing tasks in line. It ends up being very concise and works very well for PowerPoint and for short demos. All right, so first thing, just create a task group. Create a task group, call it tasks. Then what we're going to do is we're going to go from 1 to 10, and we're going to run tasks on the screen. And we're not going to do anything interesting here. We're just going to say, hello world from task n. And then as I run this, you'll see them sort of shuffled in order on the screen. And this is how you can tell that it's concurrent, because it's shuffled and not in order anymore. You lose that sense of ordering. and then I'll wait so I can go ahead and run this, close it, after I set the right startup project. Okay. Great. So there's the numbers from 0 to 10 shuffled. Not super exciting, but demonstrates the purpose. Then I wait for them. The next thing I want to do is this library called parallel invoke. So what this will do, and we have overloads up to 10 resolution because we don't have variadic templates yet. So these, you can execute both two tasks, the left task and the right task. And it's not sure what's going on here. All right, let's try this again. Yeah. This is the danger of using live code. It'll quickly go through the next demos here as we do this. So, and it just ends, yeah. There we go. So you can see the left task and the right task with parallel invoke and parallel invoke 2. The next thing that'll happen is a parallel for loop. So we can actually go in a loop from 0 to 816, I believe, and then we can do this combinable thing. I'll explain the combinable briefly. So here's my parallel for loop. Here's the combinable. So we were just talking about race conditions. What combinable does is it actually gives you some way to combine local items, and I can access a thread local item. So now this works not just in the task primitives, but in any multi-threaded application. So here I do parallel for from 0 to 100, and I access the local variable sums.local, and I can just increment it. If I tried to do this without any sort of special work, right, I'd have a race condition. I'd probably end up with some number less than 100 in this case with a single item. But when we go back over here, we can see that, in fact, I have 100. The other thing you see is these combining steps. There's 4 things in the combining steps. This shows me that on my for-way, as I go and see what's going on, I'm calling combine each, right? So for each item in this combinable, I can actually pick it up and I can interact with it on the main thread. And there was 4 of them because I'm on a 4-core box. Right, so for each of these items, I can print out how many was in them as I calculate the total. So combinable is one of the concurrent data structures we have. The next thing I want to show is some of the debugger windows. So let me go to this project. So this is an interesting project. It deadlocks. I'll just tell you that right now. And as soon as I start it, you can see there's some tasks running. When I break into it, it's going to tell me that the process is deadlocked. So I click OK. So I can pull up the threads window. How many people have done this? Pulled up the threads window with a bunch of threads. It's not very fun, is it? Well, let's see what happens. There's the threads window. Let's pull it up. That's not particularly useful, is it? There is actually some new things you can do here. You can actually search in the call stack, which is actually wonderful. If you're looking for a set of specific stacks, you can actually search and filter on it. But these are all runtime threads because they're all tasks. We have another view, though, which is called the parallel stacks window. So when I bring this guy up from debug windows parallel stacks, where did it go? There it is. Now we can see a little bit more of an interesting view. We can see all of our threads in the process. It will actually collapse those threads that are sharing stacks and show you where they again diverge. What's interesting about this is it actually has a tasks view. So for those things that are tasks, I can show you a more filtered view. Isn't that more filtered? That's good, huh? Wait for the, there we go. There we go. I can show you a more filtered view. We can see now that we have 4 tasks running. You can see that they're actually all in this event, and they're sort of waiting. If you switch thread to this stack, and you go to method view, so you can switch to frame here. And I go to method view, now I can see that actually there's multiple things waiting for them. Once I go up to event wait, pick one of the frames, I can see there's 4 tasks in this block. And of course, you can always navigate to the code. Come on. And pull this down. This is another one of those features that works best on multi-monitor. Let me just dock it. You can always navigate the code, and you can see that I'm actually just sitting here waiting for an event. This is a concurrency event. It's a manual reset event. It's another of our primitives that we provide. And when you pull up the autos window, you can actually see that we have visualized for them. So it's waiting for this event. The event isn't set. And we, in fact, know that it actually has people waiting on it. So we've done what we can to actually build these constructs and then make it so that you can actually both visualize them as you're debugging them, both in the locals window and in the sort of navigational stacks window. Okay. All right, building a parallel loop. Step 1, let's just write that we have a loop. This is parallel all of. So all of is a nifty little algorithm that was added in C++ OX. It's in algorithm in Visual Studio 2010. It just says, give me some predicate and return true if that predicate is true for all of the items in the box, right, in the collection. This is really interesting, right, because if I have a predicate that's expensive to compute, I can actually use cancellation to exit out early, right? So let's see how we do this. The first thing we have to do, of course, is get the type. So we look up the type from some iterator tapes, and we call this item type. The next thing we do is we just declare a structured task group. Now, a structured task group is a little bit different than the task group I mentioned before. The structured task group is really only useful for building parallel loops. And it's very structured in the way that it's used, and it has some very specific rules that you must follow. The task group is more general purpose. You can take that guy, you can pass it around across threads, you can schedule work on it across threads, you can wait on it across threads, you can cancel it on across threads. Task group does almost everything that you would ever want it to do. But if you're building loops like this and you want all the perf you can get, then we use structured task group and follow the rules. The next thing I do is I make a predicate. So I'm using the auto keyword. So auto for each predicate. I've got a current item. And if the predicate isn't true, cancel the task group. I'm capturing the task group by reference here. You see that I'm doing it very explicitly rather than just capturing the entire stack. Finally, I make a task out of that handle. That's because with structured task groups, you're responsible for actually managing the lifetime of that task. Where if you're using a task group, it's more freeform, and the runtime will actually handle that for you. And then I'm just going to return tasks.runAndWait not equal to canceled. So this says, run this task here on this thread that you're currently on and wait for it. Wait will actually propagate exceptions if one is thrown using exception pointer from C++ OX. Wait will return canceled if the task group was canceled, and that's what happens here. Or it will return, like, I believe it's OK or something like that, or tasks completed, if everything was just fine. So that's what it looks like here. Let's go see what it looks like in code. So I'll set my startup project this time, and I will switch it to release and make sure it's built. All right. So I've got this helper function isCarmichael. A Carmichael is sort of a pseudo-prime. It has this interesting trait that the bigger the number it is, the more expensive it is to check if it's a Carmichael. And that's why I'm using it. So if I'm checking a set of numbers from 0 to, say, n, where n gets really big, the checks at the beginning will be very cheap. The checks at the end will be very expensive. This generates an unbalanced load and makes for an interesting demo. So I'm setting n at like 30 million items or something like that. I've just got a std vector, and I'm putting the numbers from 1 to n in that vector. Then I'm just going to count them. Here I'm going to time the call of any_of. I'm going to increment the count for each item in the vector, and then I'm going to return whether or not it's true. I'll spit out the serial time on the screen. Then I'll do the same thing in parallel, right? So I'll call parallel any_of. Parallel any_of looks a lot like parallel all_of that we just saw. And I'll use the combinable object to count the sums. And then I'll time that and put it out on the screen. So let's see what happens. Two things. 281 milliseconds serial time. 46 milliseconds parallel time. I'm using getTickCount, so the resolution of this timer is approximately 15 milliseconds, give or take. Not super precise, but good enough for this. The other thing you see is that I visited about 100,000 items in the first call, the serial call, and I only visited about 30,000 items in the second call. So through that cancellation, we saw a reduction in the amount of work as well as speedups. And this is how cancellation can actually get nested, and you can actually see some benefits. Another really useful trait here, I'll have this probably at our booth over the HPC lounge the next day, is we have a UI app where we've got sort of a recursive parallel for. It looks like a concurrent depth first search where it's actually trying to find something. If you cancel that in serial, it's sort of, without doing any extra work, it sort of waits for the whole thing to finish. But because in parallel, it's nested parallel fors with cancellation sort of composed there, I can cancel it, and it just finishes right away. Right? So if I'm doing this depth first search, which takes a couple seconds, and I cancel out of it, it takes a couple seconds in serial mode, but cancellation appears instant in parallel. So it's another really, really nice thing about this composed cancellation. The next thing I wanted to show you in this is just another set here. So call this COUNTIF. So this is very similar to what we just saw, but I want to show further both the profiler, and I want to show how we can actually nest these and see additional performance. All right. So this time I'm using a concurrent vector. I'm getting the processor count. So I'm going to go from 0 to the number of processors, in this case 4. I'm going to use a concurrent vector. Now, a concurrent vector is like a vector in that it supports random access iteration, but it lets you actually append to it concurrently in a thread-safe manner and a lock-free manner, so it's very efficient. So I've now got a concurrent vector of vectors. So I'll have 4 vectors. So when I go from 0 to 4 in this case, I'm just going to create a new vector. I'm going to put the items from 0 to num items divided by 4. So we'll end up with 4 sets of numbers that are equal in number, but when I run isCarmichael on them, the ones at the beginning are very fast to execute, and the ones at the end are very slow to execute. What we're trying to show here is that not all workloads are even, right? What we want people to focus on is like, here's my problem. Here's how I'm going to stitch these algorithms together. And if I'm not able to work steal between the tasks, if I'm not able to compose that parallelism, if I'm not able to say, hey, here's my algorithm. Right here is at the point when I call it, this is when I want to talk about concurrency. Then that algorithm and that library call that we all build isn't as reusable because I can't say, well, I'm going to use it in a UI app. I'm going to turn around and I'm going to use it in a server app. I'm going to use it in a service. I'm going to run it on my netbook. I'm going to run it on my quad core. I'm going to run it on my dual core. It's really important that we not actually bind this concurrency into the expression, that we in fact be able to say, like, here's all the tasks. We leave it to the runtime to make sure that that task overhead is as small as we can make it. So here's what we're doing. We're going to call transform. So transform takes the vectors in this case, puts them into another vector of integers. Again, very naive, simple things. And we're just going to sum them up. And we're going to say, how many integers are there in that vector you gave me that are Carmichael's? So we're going to stick that sum in that other vector. And we're going to time it. And then we're going to call accumulate, so reduce, and just total it up. Very straightforward. And then we'll print out the time, print out how many Carmichaels there are. And now we're going to do the same thing in parallel. So we'll call parallel transform. This is something that the team put together, and it's in our sample pack. It works just like transform, but it operates in parallel. Countif, which is very simple and very much like any of or all of that I just showed you, and parallel accumulate, which is also in the sample pack. So stitch these together. This one, sorry, doesn't have a parallel countif, right? So this is a sequential call inside. And the third call inside, we have parallel transform, parallel countif, and parallel accumulate. And when we run this, what we should see, in fact, is improved scalability at each point. And I'm crossing my fingers because occasionally something wakes up and does something. It's waiting for me to input. And in fact, we see this. So it takes about 4 seconds serial time. When countif is parallelized, I get a pretty good speed up at 1.3 seconds. But when countif is parallelized as well, now I get basically a linear speed up, and this is wonderful. This is just by describing these tasks and being able to say, like, here's a parallel loop, here's a parallel loop, here's a parallel loop. Stitch them all together, compose them. Don't worry about this thing scaling because it's going to be OK most of the time. It's never, of course, that simple, but that's the ideal that we want everybody to be able to work towards. So let's see this in the profiler. You can actually see this. This is a wonderful set of features we've added to the Visual Studio Profiler that actually let you peer into your multi-threaded application and see what's going on. It works really well in these kind of cases where you're CPU bound. So I'll pretend to launch it here. And if I was doing this for real, I would say, start a new concurrency profiling session and visualize the behavior of a multi-threaded application. But I'm not going to do that. I've already got a trace that I took earlier. The symbols are all loaded. We don't have to wait. We can just look at it and navigate around it. It's right here. So when you first pull this thing up and you look at the CPU view, you get sort of this histogram, say, of time over how much of your system you're using. That orange stuff at the very top with the diagonal lines, that's interference. So that's stuff that's going on that's not related to my process. When I'm seeing green, this is telling me how many cores I'm actually burning actively at this time. So you can see there's a whole bunch of time where I got peaks at 4 processors being utilized. And there's some stuff where, really nothing was happening. And anytime you see this red, that's synchronization. So if you're expecting to see high throughput and you see a lot of gray or you see a lot of red and gray, then that's a potential problem. So let's zoom out and go back in. This is what that second case looked like where we did parallel transform, but a serial countif inside followed by a parallel accumulate. You can see that we got pretty good scalability at first, But then we had some places here where it wasn't so good. You can go to now the threads view, and I'll show this in the context of basically this application. But if you're taking your application, you're trying to figure out why a thread isn't making forward progress, why something is blocked, it will actually show you with the call stacks enabled when a thread is blocked and when it comes back alive and which thread unblocked it, right? So if you have a particular thread that's waiting on some IO or waiting for an event, you can, I keep using the wrong mouse here, you can actually click the region and it'll draw a little gold arrow to the call stack that unblocked it. And this is incredibly powerful and incredibly useful. Let me get this in full screen mode here. So sort by execution time. When I look at a trace like this, and I know that it's a parallel loop, you sort of see this pattern where you're not getting skied up and you see this trailing off the end. That's a big signal that the loop actually could be decomposed again and there's more opportunity for parallelism. We're lucky in this case that the inner loop is something that's very easily parallelized. But when you see this pattern of, I'm expecting to see a parallel loop, I'm expecting to see high throughput, but I'm sort of petering off at the end, that's a signal that there's more opportunity here and there's more that can be done. And in fact, if you take this app and you put it on a higher core count box, it's actually going to scale worse because of that trailing off at the end. But over here is the other side of it. And there's still some stuff going on. I'm still not getting 4 threads during this trace because there was some activity. But it's actually looking pretty good, and I'm actually getting pretty good throughput. And at the end of this, I don't have the same sort of petering off. You can see even at the end here, I'm getting basically 3 cores active at the same time rather than this long delayed piece. The other thing you can sort of see here, these blue lines. What are these blue lines? Well, we actually have instrumentation. So if you call concurrency : enable tracing, it'll draw markers, and you can see where your for each is without having to search for it. And of course, as you would expect, you can click on a region, zoom way into it if you want. You can measure this stuff too, which is kind of cool. See how long a particular region took. And you have a stack trace, and you can always go straight to your code from the stack trace. All right, so we've really done everything we can to really integrate this. And this is useful both in sort of these task parallelism examples that I'm showing, but also in your existing multi-threaded application today. There's no reason that you can't get a lot of value out of this. Okay. Great. So we did that. So that in 30 minutes or less is the parallel pattern library. We can talk about tasks. We can talk about parallel loops, parallel for each, parallel invoke. I didn't talk too much about the synchronization primitives. I'll have another example of one of the locks. But we have cooperative locks. And when we say cooperative, and Dana again will talk about this more, this is a signal to the runtime that you're about to block. So I'm waiting for this lock. The runtime now knows that I'm blocked and waiting for this lock. And if you have other tasks described, we can use that opportunity to run them rather than giving up your quantum back to the OS to run some other process's work. You can keep that in your own process. So a reader writer lock, a critical section, and an event. We have 3 concurrent containers that are in the box. We have a concurrent queue. So this is very straightforward. You can call push on it. You can call try pop on it. There's sort of unthread safe iteration. So when you know you're all done with your append and adds, you can actually iterate over it like a container. Concurrent vector, which offers random access iteration while you're actually appending to it. And combinable. And the URL below is the sample pack. There are many more algorithms up there. There's some good examples. And I encourage you to check the documentation. It's actually relatively thorough and very good at explaining these concepts. Okay. Switching over to the next programming model, the asynchronous agents library. So what is the asynchronous agents library, and what is an agent? An agent is an implementation of the actor pattern. It's a very coarse-grained component in your application. So if you're thinking about a model view controller application, it might be a model. It might be a view. It might be a controller. Right? It's these potentially long-living, I won't necessarily say long-running, but long-living application that has some state you want to manage with it. It gives you some benefits because you can actually take that agent, have some tasks in it, and move those tasks and those threads that are part of that agent and the state in it and actually attach it to the agent rather than, say, letting them live in TLS and being somewhat implicit, or even worse, sticking them in a global somewhere. Sources and targets are the next major concept in the agents library. So we have an actor. Actors communicate through message passing. Sources generate messages, and targets receive messages. You can take sources and targets, and you can connect them together, source to target. When you do this, it becomes a parallel pipeline that preserves ordering, where each stage in the pipeline is actually a task. So if your pipeline is 4 deep, you can have 4 tasks. If they're all busy, that's using all 4 cores on a 4-way. And finally, we have send and receive. So you can send messages. You can send messages asynchronously with asend. You can receive messages, which is a blocking call, or you can use try receive, which is a non-blocking call to check to see if there's a message. And now let's go back to Visual Studio, and we'll do some very naive, very simple pipelining with this work. And we'll see how they look. All right. So I'm using the agents library. It's in agents.h, not surprisingly. The first thing I'm going to do here is I'm going to declare this little function called absolute value. It doesn't do much. It takes an input, it returns an output, and it prints on the screen that it's computing the absolute value of whatever it did. And then it returns the absolute value of this. I'm going to create a message block called a transformer. So a transformer is a particular kind of message block that takes a type A, transforms it into a type B via a task or a functor that you construct it with. In this case, we construct it with absolute value. The next one I'm going to use is another transformer. This one's called square roots. I'm going to give it a lambda. It takes a double, prints out on the screen that it's doing something, and returns a square root. Again, not super interesting. Squares, which squares it. Negates, which negates this. I have a vector of numbers. This is just a stood vector. So I've got a parallel pipeline. I'm going to use a non-thread safe vector inside this pipeline. Now this is important because as we're sending messages to the pipeline, the runtime and the agents library is going to guarantee that there's actually only one task running per stage in that pipeline at a time. So if you've got a transformer, if you send it a lot of messages, they're going to queue up in a queue, and they're going to be processed sequentially. But what this allows you to actually do is it actually allows you to act in a single-threaded manner inside your message block, which makes things a heck of a lot easier. So now I'm creating a call. A call is a message sync. It takes a double, runs a task on it, doesn't return anything, and I'm just adding the number I get to this vector. The next thing I want to do is I want to link them together. So I'm going to take my squares, I'm going to link it to square roots. I'm going to take square roots, I'm going to link it to negates. I'm going to take negates, link it to absolute values. You all see where this is going. And I'm going to take it absolute and link it to that call. In effect, I've done nothing when I send it 10 items. So I go from 0 to 10, send these messages to it, and I sure hope on the other end that they come out in order, the numbers 0 to 10. So let's make sure this is a startup project again. So I'm going to run it. And you can see from the garbled mix at the top that it's parallel because the ordering doesn't look like there's any sanity to it, but there is. And where was the for each? And you can see at the bottom that I've printed out on the screen the numbers from 0 to 9 in order, preserved, even though I've just sent them through this parallel pipeline. So this is really wonderful because it actually allows us to do things like process files in order, process streams of data in order, send a path, a file path, down a pipeline, and then open that file, and then do some processing on that file. Sometimes these things are expensive, sometimes they aren't. But I can take these decorator-style patterns, these streaming patterns, and I can now parallelize them, and I can keep that ordering, and I can keep the single-threaded version of it in some cases, as long as I'm relatively careful and relatively sane. And I can add this where I want to, right? It's not this sort of global thing that I have to do. Anyways. The other thing I want to show here is, again, in the locals window. You can see that we have visualizers for this unbounded buffer. If that's still up, good. The unprocessed messages, that looks kind of like a queue because it's a queue of messages. The messages that it's storing looks kind of like a queue. It's empty because I broke on the first one. If I break again a couple times. Let's see. Then it dies on me. Let's see. I stepped out of the stack. I'm going to move on. But if I broke again, you'd actually see that the messages were queued up in the unbounded buffer, and you could actually see them in order still, so, which is wonderful. Great. So that was a pipeline. Now let's talk about agents. So as I mentioned, the agent provides a model for state and lifetime management. So you have this thing that you can declare on the stack or on the heap or whatever called an agent, and you can actually manage that and hold on to it. It does provide a migration path for threads and thread local state. The imaging demo that we showed at the beginning is actually built on both the agents library and the parallel pattern library. It's using both. But there are very much agents floating around doing things and sort of managing the processes. So to build an agent, you derive from the base class agent. The guidance is to expose only sources and targets publicly. So this is an item that, this agent is this thing that you want to live in a concurrent world.
And we want to expose these message blocks. You can actually send a message to it, receive a message from it, send another message to it, link agents together. And in that way, you can keep the processing going without actually necessarily keeping a stack running the entire time, and without actually doing a bunch of really messed up, crazy stuff that can kind of happen as you try and take your threads and do cross-thread communication. So it looks like this in code. So I create an actor, I drive it from agent. I might have an overwrite buffer of integers. So I showed you transform and call an unbounded buffer. Overwrite buffer will store a single value and always provide a copy of that value of whatever type that you use. The other type I haven't shown is single assignment, which you can write to once, and then it will forever produce that copy. I've got a transformer and output buffer. I'm only going to expose sources and targets. So iSource is the base class. So I can actually take an iSource. It's not a COM object. And I can actually hook that up to the transformer, and I can actually take an iTarget and hook that up to the overwrite buffer. So when I link the transformer to the output buffer, then I have this little tiny pipeline inside that I know about But all the rest of the world knows is that I have something that produces ints and something that consumes ints. And they don't know whether they're the same message block or different message blocks, or in fact, you sent them the message block that they talk to. All you know is that this produces ints and it consumes ints. And it's a very wonderful thing because it lets you add the places into it where you want to actually be really careful with pointers and things like that. You don't have to do this. It will be copy constructed by default. And so when you need the efficiency and the risk of adding pointers, you can add that to it, but it's not necessarily there. Okay. So now I want to do a demo about visualizing race conditions. I know we just had a talk for those. How many people were here last session? Just curious. So a good chunk of folks. So this is what a race condition could look like. First, I'll do it in PowerPoint, and then I'll show you some running code which does it. I might have a widget class with 2 data members, width and height. I might be able to get that width and get that height from that widget, and set that width and set that height from that widget. So you can easily imagine that if I'm trying to say, set the state from another thread, that I'm going to have to lock because there's going to be race conditions if multiple things are trying to set this widget together. And this might look like, it might look like this. So here's these widgets. They're both squares, right? The one at the top will take on whatever attributes the one at the bottom has when it hits it. If I add another square, this one is small, the other one's big. If things are working correctly, then I'll have small squares or large squares. If I screw up, I'll have a rectangle. Like this. That's a race condition in its simplest form. Lots of other really nasty stuff can happen when you get race conditions, but this is one of the more benign cases. Well, how am I going to fix this? Let's add a lock, right? This is how we do it. We add locks. So let's add a reader-writer lock. We'll take a scoped lock using the scoped lock on the reader-writer lock. So this is concurrency's reader-writer lock. Both the critical section and the reader-writer lock support the lock concept. So if you're using Boost, or you have some libraries from C++ OX that have lock guard, they'll just work, which is wonderful. We have the scoped lock directly on the class. So when this lock guard destructs, it'll release the lock. So there we go. I have a lock around get width, set height, and set width. How many people think this actually fixes the problem? Nobody. It doesn't. Right? It's never this easy. Even though I've added a lock. It's an unsafe interface. Because we never have APIs that like, man, I just call it once. You got to like call API 1, then API 2, then API 3, and then you sort of apply that. That's kind of how the real world works. We can always fix it by adding more locks and say, all right, I'm going to acquire the global lock for this object and know that I'm going to begin the operations on it and then end the operations on it. Or we can coordinate this with message blocks. There's 2 pieces to this. Message blocks are easy because they're sort of in the box and do this implicitly. You can, of course, do this without message blocks. But the refactoring is twofold. You see 2 pieces of refactorings. The first and most important thing is we have this single API at the bottom called update dimensions. So I'm just going to do one operation on this. Set the width and height together. The other piece, and this is just as important, is now I have an overwrite buffer of dimensions. The problem with actually having those exposed interfaces is that the data members aren't actually thread safe. Overwrite buffer is thread safe by default. There's no operations you can do on overwrite buffer that are not thread safe, right? There's always opportunity to do things on, say, volatile longs and volatile ints that are not thread safe. This is one of the major compelling reasons why the C++ OX atomics library is so important, because it gives you a way to talk about that volatile long, right? And interlocked increment and interlocked decrement, where here's this atomic long, and I can just increment it and decrement it, and I don't need to worry about someone forgetting to do the right thing. And it's the same thing with the overwrite buffer or the single assignment. The data member is just thread safe.
So let's switch over to this fun little demo and hopefully visualize it. So this is the ray tracer. The ray tracer only shows spheres. It doesn't know how to do cubes and rectangles and squares. This is the threaded version, and it's not thread safe. But it's OK, because they're going at different frequencies, and you don't see the rays. Right? So if we ever end up with a big red ball or a small blue ball, we've got a problem. Right? But this is OK, right? Because even though it's that first locked interface where they're not thread safe, it looks like we don't have problems. But as we all know, sometimes different machines, we think stuff is fine, but if you run it on a different machine, you get different timing characteristics. And sooner or later, you'll end up with that little blue ball or the big red ball. I'm trying to see if the big red ball will actually show up. It does sometimes. Right? And it's just a matter of timing. And it doesn't, here it's because I've timed the balls, right? But it could be anything. They could be running an application. They could have a special kind of machine, right, that's running. You just never know about these race conditions. And it's incredibly hard to find them. Right? You have to either use tools like we saw before, which take a long time to run, or you have to spend a lot of time staring at code and convincing yourself that there isn't a problem. Someone's done that before. And this kind of pattern actually helps. So where you can use this, it can make it easier. Because I can look at this and say, yeah, there's no races here. Right? I still need to be careful with the widget dimensions object. But this particular class and this interface on this class is safe. And it's relatively easy to see without a lot of thought. I don't have to worry about giving it to someone else and having them use it. I don't have to worry about them, poking on this override buffer by adding a method. They can always still do some things with the instance, but it's much safer than that previous method. So in summary, we have message blocks for storing data. So this is the unbounded buffer. It's kind of like a queue. It just keeps storing messages until you run out of memory, or you consume them. Preferably, you consume them. We have an overwrite buffer, which always stores a single method and message of type T, and we have a single assignment buffer, which you can assign to once, and will produce that message multiple times. We have message blocks that will actually transform the data or pipeline the tasks. We have a transformer. We have a call. We have message blocks for joining data. So rather than calling wait for multiple objects, you can do a join on a set of message blocks and just get the data you were waiting for. Because after you do wait for multiple objects, OK, here's a set of events. Those events all usually go back to some piece of data. Then you have to look up the data. But you can just join on the data and get the data. You can join greedily or optimistically and say, I'm going to take that. Or you can actually do a two-phase commit join. So if you have multiple overlapping joins, you can let the one succeed that is truly fulfilled. We also, in our sample pack, have this thing called join transform, which says, hey, the thing you always do after you join is run some work. So let's just codify that into a pattern. So join a bunch of data together and run a task on it. And of course, the cooperative send and receive helper functions for actually sending messages and receiving messages. All right, so this leaves about 10 minutes for questions. This is a summary. I talked about everything on the right side in the top half here. We have lots of talks at PDC this week covering all this stuff. Dana is going to be talking about SVR 10 on Thursday morning. SVR 18 is going on, I believe, right after this talk. It should be another really good one. And there's a bunch of chalk talks. We'll be at the HPC booth. We'll also have folks over by the Windows C++, or the Visual C++ booth as well. So please come by. And there will be many folks at Ask the Experts as well Wednesday night. All right. Thanks. Yeah.
Do you have any intent intention to add concurrent map, hash map?
Do we have any intention to add concurrent hash map or concurrent unordered map? It's something that we're talking about, and we're considering. It's not going to show up in Dev 10, but we should talk about this more next week, Christian. Yeah. So the PPL and the agents library are implemented as template header files. They're sprinkled throughout them. There's R-value references and lambdas. So you have to have the 2010 compiler. The layer at the concurrency runtime itself doesn't use any of that stuff. The concurrency runtime itself doesn't have R-value references or lambdas or any of the C++ OX or Dev 10 particular features. So you could probably, if you really wanted to, get away with some of that there. Yeah, that's right. Yeah. Right. I've looked at it a little bit in the last month, but I've looked at a bunch of stuff since then, and so this is probably a conversation best to have in a little bit.
Hard to combine that with this, because it's a totally different set.
Right. So the question is how do I combine this with something like Blitz? So this is STL style. As far as building your own loops, it's very possible to build, like, say, a parallel for or a parallel, set operation on top of something else, on top of structured task group. When you look at parallel for and parallel for each and parallel reduce, they're all built on top of structured task groups and tasks. So to the extent that you can actually say, here's this operation that I want to sort of decompose into sub-operations, it will parallelize. You just will likely have to build additional interfaces on top of it. The source is split between the runtime and the header file. So when you get down to a structured task group, that's sort of as deep as you can see in the template header file, but we do ship the source for the runtime with the CRT because it's just part of the CRT. So as you install Visual Studio 2010, you can debug and see what's going on. But in general, when I have folks say, hey, I want to build, algorithm foo, how should I do it? We say either, use structured task group and tasks. If necessary, sometimes go down to the runtime itself, where we have some task scheduling primitives that still cooperate with the runtime and are still very low overhead. Or you're building something a little bit higher level like the agents library. I'm guessing, as Blitz is kind of like feeding back into my head, I'm guessing the structured task group would be the place to start with that. But you would likely have to build on top of it. I don't know. Yeah. So, any more questions? Okay, there. Okay, so for the question is deployment. So all the binary code is just inside MSVCR 100, MSVCP 100. So when you install the Dev 10 redist, you don't have to do any extra work. We support the same OSs that VS supports, so x86, x64, down to XP. And there was a question here. So we let Windows do that. Windows does a pretty good job if you have a bunch of threads scheduled across process of round-robining between them. When we actually lay out our threads, we'll look at the hardware, we'll look at the node structure and sort of affinitize things in a sane manner. We affinitize things to nodes. What? And come on Thursday, and Dana will talk a lot about this for an hour. So the top is lighting up Windows. It's SVR10 or SRV10. It's Thursday morning at 8:30 in this room. It was earlier. There is, I think, I don't know. Look at your calendar. I can't keep. Pedro Teixeira is doing a talk, I believe, after this. Is he not doing it? What? He's doing it after you now? So that changed. All right. So Dana's looking it up. 408B, Thursday at 11. Is that right, Pedro?
Yeah,
Thursday at 10.
Thursday at 10 is Saturday 18, 408 Alpha.
Okay. Did you get that? Thursday
Bravo and 408 Alpha.
right, Thursday at 10 and Thursday at 11.
10. 8:30 and 10.
8:30 and 10. Okay. All right. Anyone else? All right.